So hello everyone, welcome to the third session. Our next speaker is Elad Hoffer. He's a principal engineer at Habana Labs. He did his PhD at the Technion with Daniel Sudri. He has lots of groundbreaking works in deep learning, both in quantization and implicit bias. Before we will talk, I want to thank again our sponsors for this event. We're very thankful for them for enabling us to have it. We thank Apple and Rafael, the AI and data science centers at the Technion and Tel Aviv University, and also the ACRC center at the Technion. So welcome, Elad.
Okay, so hi everyone. Thanks for the introduction and for inviting me. So I'm from Habana Labs. I will cover work done also with Daniel Sudri's lab from Technion, and I will talk about training deep learning models with low precision floating point. So just as a quick recap, just to get the terminology right. I'm talking about deep learning workloads. First up is the forward pass. We have a series of sequential computation, also known as layers. Layers usually have optimized parameters or weights, and we have a lot of common computational patterns. First one and the most common one is matrix-to-matrix multiplication, or GEM. Which account usually for most of the workload. We have pointwise nonlinear function and reduction ops, and finally an objective function, a loss function that is computed. To train a model, we also need to perform a backward pass, in which we compute the gradient of the loss, and then use chain rule to compute the gradients for all layers. Okay, this is also known as backpropagation. Finally, we can accumulate the gradient of the weights with respect to the loss and average across the batch, and then use them to update the weights for the next step. Okay, just notice that the backprop is a linear operation, which we'll use later. Some additional useful facts that we might need to consider. Training a neural network is an inherently noisy process. Okay. You sample your data, you augment your examples, maybe use dropout. There's a lot of noise involved. Also, common numerical metrics may be misleading. So, for example, if you implement a new version of a known op, and you measure just the error of that op, that might not be enough. You might need to, for example, train the whole network just to be sure that you got it right. And finally, training is a dynamic process. The statistics might change throughout training, and one thing that worked early on might not work later in the training. So why should we quantize at all? Why should we use low precision formats? So quantization allows us to manipulate data at lower number of bits. We can use that to accelerate computation if we have the suitable hardware. For example, if we have faster multipliers, or we can use less compute cycles in our hardware, we can make the network run faster. We can also reduce bandwidth requirements with respect to the tensors themselves. This is a common bottleneck for many workloads with the available hardware. Also, I should mention, we can reduce the memory footprint itself, which is also a pain. And we can also make computation more efficient. Okay, we can reduce power area, improve the computational utilization by allowing larger models with less devices. And this can also further improve performance because, for example, we can increase frequency if we didn't reach the power limitation we have. So I'm going to talk about floating point representation. This is just a simplified version of a floating point. We have exponent bits that correspond to the power of 2 part of the number, and mantissa bits for the fractional part. A lot of people think about it as a dynamic range represented by the exponent, and precision represented by the mantissa. So a bit of history. Traditional scientific computing favored precision over range. So scientists used to use FP32, maybe even FP64, which had a wider mantissa. But that is clearly not the case for deep learning. So we know for a while now that a deep learning application can make do with lower precision. And FP16, using only 16 bits, is accelerated since 2016 by GPUs. It required several training adjustments to how we train a network. Later, BF16 was introduced and specifically targeted deep learning application. So it allowed models with better accuracy and less adjustments. And this is probably due to the fact that it didn't reduce the exponent bits, as you can see here. It used the same number of exponent bits as FP32. And today, both FP16 and BF16 are accelerated on almost all modern hardware. So other insights that people understood over the years, first of all, weights and activations seem to be quantized easily, in the sense that we can convert weights and activations to 8-bit integers and get essentially no degradation. So this is widely used in inference. And there are even successful implementation in 4-bit, even down to 2 bits of precision. Gradients, compared to that, have a wide dynamic range. This means that instead of integers, usually we prefer to represent them as floating points. And as you saw earlier, floating points with wider dynamic range. So BF16 is better than FP16 in that respect. And in general, they are harder to quantize. And finally, there are several ops that are known to be hard to quantize, like normalization, softmax, part of the optimizers. We know that they are hard to quantize, and we usually prefer to keep them at high or even FP32 precision. So we are now entering the era of FP8 training. So I'm not sure if you're familiar, but new hardware like Gaudi 2 from Habana, H100 from NVIDIA have support for FP8 training with all the benefits that I showed you earlier. Yet it is still challenging to make network converge at FP8. And we were interested to find ways on how to make that process more easy and to make network trained with FP8 precision both quicker and more easily trained, and to get better results. Previous methods usually used trial and error, which is very time consuming and a lot of effort. So our first idea, and this was published 2 years ago at iClear. We had an insight that different tensors inside the network and inside the network training are distributed differently. So for example, activations, weights, and gradient of weights are usually distributed like Gaussian or Laplace-like distribution. This means that most of the mass of value is distributed across the mean. Compared to them, gradients of activations, or neural gradients as we call them, are distributed like a log normal distribution. So this kind of distribution has a long tail where you can find very large values, like 3 orders of magnitude larger than the mean. Okay, so these are 2 very distinct distributions. By the way, activations from attention from transformer models can sometimes be Gaussian-like and sometimes be log normal-like. Depends on the model size and shape. So what we can do, what can we do with this kind of assumption on distribution? First of all, we can determine what is the right format. So given an FP8 requirement, we can try to find what is the right number of exponent bits we need to represent. So what we did is to write the error function, the relative error function of the quantizer, and then we can minimize the relative error and find for a given statistics what is the right number of exponents we need to represent that number. And using that method, we found that there are 2 different types of FP8 that are suitable for different types of tensors. So FP8 152 with 5 bits of exponent and a wider dynamic range is suitable for the neural gradients, the gradients with respect to a layer. While FP8 143, the shorter dynamic range, but slightly more precision, is better for weights and activations which have Gaussian-like nature. So we now have many types of data types available, ranging from FP32 to the 2 FP8 formats I showed you. And you can see here that in FP8, we suffer both the loss of precision and dynamic range. We lost exponent bits and mantissa bits. And there are a few issues that arise. The first one we want to solve is the loss of dynamic range, which I showed earlier. That is probably the most important one for deep learning applications. So FP8, both formats suffer from dynamic range loss, but FP8 152 is somewhat similar to FP16 in the sense that they both have the same number of exponent bits. So we wondered, will common practices from FP16 training, will they suffice for FP8 training? And the one most widely used is loss scaling, which I'll show next. And we wonder whether this will be enough. So what is loss scaling? So assuming you want to compute the gradients of a specific layer, this layer the gradients have a range of values, but these values might not be represented in the low precision format because of the loss of range. And these values either be underflowed or clamped to 0 or the minimum val, but you will lose information. So one thing that people have done over the years is use loss scaling. With loss scaling, you simply multiply the loss with a large value, a loss scale, and use the linear property of the gradient so that the values, the range of values, will move accordingly in all gradient layers. So now this range can be represented using the low precision format. And this worked and still works for FP16 training. And of course, you can just remove the loss scale at the end by dividing the weight gradients with the same loss scale factor. But what happens when you have several possible ranges in the network? When you shorten the dynamic range even further or reduce precision, which is required? So now this is much tougher to find. And you might not be able to get a single loss scale that will work for all the different ranges you might find in the network. And indeed, what we found is simply by measuring training regime, we found that indeed statistics can vary across layers and also across time. You can see here that these are the statistics of the log normal distribution. And you can see that there's a large difference between layers. And some of these layers change throughout training. This is very hard to catch with a single scaling factor. We need to find something better than low scale. The easiest method we found, we can simply measure each one of the tensors and scale to fit the represented values. So we can measure the maximum absolute value of a tensor and then shift it by shifting the exponent to be represented in the low precision format. And this actually works for a lot of different formats and for a lot of different tensor types because it doesn't assume anything about the distribution. Also, you might wonder that there's an additional overhead, right, measuring these tensors. But what we found is that we can estimate the maximum value by using past measurements and by that reducing the overhead needed. And this works nicely, and we can get networks to converge with a scale per tensor. And network that previously with a single low scaling factor failed, now they work and won't require any additional modifications. Next, there's a problem of bias. So to quantize, we must use a rounding scheme. The most common one is round to nearest, where for each value, you quantize to the nearest bin in the low precision format. But this kind of rounding scheme introduces bias because now there are certain values that are overrepresented compared to others. So, and another benefit we considered is that if we have an unbiased quantizer, then the most common op, which is a dot product, has the nice property that as the shared dimension grows, the expected error will drop. So you'll get better and better accuracy as the shared dimension grows, as long as you have an unbiased quantizer. So instead of the round to nearest, we considered a stochastic rounding scheme. Now each value will be truncated to either one of two bins with a probability proportional to the distance between them. Another view is that stochastic rounding is simply round to nearest if we injected noise that is proportional to the number or to the exponent. So again, we're faced with a trade-off. Round to nearest has the lowest error. The mean square error is lowest for round to nearest quantizer. But stochastic rounding, as we know, is unbiased. So we have these two properties. And what we found is, again, there's a trade-off in how we train a network. It turns out that while for forward pass, we should use round to nearest, we get better results if we keep the most of our precision. But for the backward pass, it turns out that bias or reducing the bias is more important than the precision we have. So it turns out that you need to use two different rounding schemes. And here you can see it. This is from a paper published this year in iClear. These are results for FP4. We found that this becomes crucial as you reduce the available precision you have. So just to summarize, we've not yet reached the limits of FP8 quantization. We moved from FP32 to 16-bit formats. We're now at the phase of FP8 adoption, and we can see a future for FP4 maybe below that. Some useful tools you should keep in mind. You should know your distribution. You should keep in mind that activation, weights, gradients, maybe even certain layers may quantize differently. And my prediction is that future hardware accelerated will be heterogeneous with respect to precision. You might see integers multiplying with floating points, maybe floating point without mantissa. But there's a clear case for heterogeneous formats. Second is that you should measure and scale your tensors to balance between the dynamic range and precision you have. And finally, another trade-off is to bias between to trade-off between bias and error. We found benefit for stochastic rounding schemes, especially for the backward pass. So that's all. Thank you very much.